Okay, so let us start our discussion today on the uh, records from digital accelerograph. So those are the most of the installations uh, nowadays are from digital accelerograph. So digital accelerographs, the design, I will get into little rudimentary concepts of the design of digital accelegraph, how they are different from analog accelegraph that we discussed in our previous discussion. So what is different in digital accelegraph is that the sensors primarily we look at the sensor that are of force balance type. So that's the main sensor. Uh, Predominantly digital accelerographs, they deploy this force balance accelerometers as the sensor. Now, the force balanced accelerometer is different from what we considered about the analog accelegraph, which is simple pendulum, and we measure the relative displacement, and that relative displacement with respect to base is proportional to the base acceleration for certain frequency range. In case of force balanced accelerometer, it is essentially a small mass is suspended from a system. So that is of course true with similar to what we have for analog accelegraph. So it is a suspension. So there is a spring and the mass is there, and the one thing major difference with respect to an analog instruments is, for analog instruments we try to keep the damping in this system, the pendulum, to be approximately 70% critical, and that 70% damping is required to ensure that the phase difference, because whenever we have a response, it's not only amplitude amplification, the phase also gets modified. So for 70% damping, we have a very nice linear relationship with the phase with respect to frequency. So phase shift happens as a linear function of the frequency in case of uh, mechanical pendulum. So then that actually implies the implication of that simple observation is that there is no phase distortion in the record. Otherwise, different frequencies would be shifted by different amounts, and then there will be a distortion of the waveform, and the recorded waveform will not be a true representation of the base motion. But if the phases are shifting uh, by a constant multiple of the frequency, then obviously it's a delayed replay of the base motion. So there is no distortion in the waveform itself, and therefore it is essential that the damping ratio of the pendulum should be around 70% as far as possible to minimize the phase distortions. But in this case, for force balance accelerometers, we actually try to keep damping as small as possible. So that's a major difference. Very low damping, and the reason for that is we do not actually allow any motion. The pendulum itself does not vibrate. Uh, what happens is there is a feedback loop there is a power and some power source. So there is a sensor here. I mean, because this is kept in a electromagnetic field. So whenever there is a motion, there is a change in electromagnetic field, and the sensor will pick up that change, and it will also calculate what is the because this mass is of course a known quantity, because that's a designed system, so we know exactly what is the mass of the system, and by virtue of knowing what is the change in the electromagnetic field by the motion, we know exactly what is the force that will be required to negate the motion of the mass exactly. So we exactly put opposite force to the mass, inertial mass, so that it is held in position, right? So inertial mass is held in null position. So this is the force, additional force that is generated by a servo motor. So that is an external, there is a power source inside, and that powers the servo motor, and that feedback system, feedback loop, the controller will determine exactly what amount of force to be is required to keep this mass in null position. And by knowing this force that is being applied, and knowing the mass of this inertial mass, value of the mass m, we can divide the force by this mass, and we know what is the uh, acceleration of the mass, right? And that acceleration is what is the base acceleration or the total acceleration of the pendulum. And this spring is of course kept very, very high. So very stiff spring, so that whatever is the motion of the base, that is same as the motion of the mass, right? So that's how the force balance accelerometer works. So we really do not allow much of the movement to take place, and everything is done electronically through the electromagnetic field and sensors, and the motion of the mass is not really allowed to move, and everything happens as you know, the sensor signals, electromagnetic waves are very, very fast, so the delay in the decision sensing and the actuation is actually very, very small, much smaller than our least count of time that we use in this system. So natural frequency of this oscillator is of the order of 200 hertz or more, so we can faithfully retrieve the information about very easily about 75 hertz or so. So natural frequency is of the order of 200 hertz, and useful frequency range is 0 to probably 75 hertz. So we can extract information in this range. So this 0 is still a question mark, we don't really, I mean, theoretically the response is of course flat from 0 hertz, but the problem is now we come to the recording. This sensor is always the system is always on, but there are two recording media. One is a buffer short term recording, and two is a long term recording. What is done is short term recording is a kind of buffer recording. It will keep on, I mean, all of them are actually solid state memories, solid state storage devices. So it's a buffer memory. It will keep on start recording and then it will keep on writing, and after it is exhausted, it will again overwrite the system, the same memory. So it keeps on writing and rewriting, writing and rewriting all the time, right? So we call it buffer storage. And it is being writing in cycles. So it just keeps on writing it, and then after the cycle is complete, it will just overwrite whatever was there earlier. Now, obviously this is a small segment. We don't need a very long memory. Of course, we can decide how much to use it. And long-term recording is the permanent storage. This does not get deleted unless we specifically delete the whatever is the content of this storage. So what happens is when the instrument is sitting idle on the platform, on the base, right? So the unit is sitting in this installed on the base wherever the station. It is powered on and it keeps on recording in this buffer storage till the time when the base motion or the acceleration exceeds a particular threshold that is preset in the system parameters. It will move some part of this pre-event memory that we call into the permanent storage, and then start recording from that point onwards on the permanent storage, right? So permanent storage will have some pre-event I should say pre-trigger signal, and then post-trigger signal, that is the main event. Right, so this is patched up, and after the signal, the base acceleration that we are recording, if it again falls below the threshold, then again it goes back to this buffer storage, and some part of the post event after this low trigger has been kicked in. So some part of the post event is also patched up. Post event signal. Now the length of this pre-event and post-event, that can be set user specified. So generally you will find mostly this is pre-event is about 20 second, post-event is about 10 second. But that's user choice actually. You can use whatever is required. So that actually depends on the site condition and what kind of analysis we are doing. But I understand that all NHPC stations, they are on continuous record mode, so you do not have to bother about these pre-event and post-event settings. But in general, when it is stored, when it is deployed at a remote location which is not easily accessible, then the storage is of course a very precious commodity. You do not want it to be full without any significant information, and therefore this particular design is very valuable. This system, the accelerograph, will keep on recording in this buffer storage until some interesting signal happens, some interesting signal is event is triggered, and then that signal, main event signal that is of interest, is recorded, is moved to the permanent storage along with the suitable portion of the pre-event and post-event signal. So that actually patches up the total signal as something like this. So this is what we call as pre-event, and this is the main event, and this subsequently is post-event. So now one major problem that was that we had with analog accelerograph is in a way circumvented, in that we have not we do not have any idea about the starting of the event. So in this case, in case of digital accelerograph, we know that event has started somewhere here. We do have some information somewhere here. The event in this pre-event portion is the start of the location, start of the event, start of the earthquake. And similarly, somewhere in this post-event portion, there is end of the event when the vibration, earth vibration because of the earthquake actually cease. Now the point is, how do I determine those origin, and end time? So how do I determine that? So for this, we actually obviously we cannot be very precise in that. We can only have some approximation, and that is based on ratios of two averages. Short term average and long term average. So STA divided by LTA. So this STA is actually the time window. How much window do I take? So maybe I can take let's say I define short STA window as about 1 second, and let's say LTA window to be about 5 seconds. So I compute this ratio STA versus LTA. So you will find that for the duration for the segment where there is no earthquake activity, then this STA LTA ratio is of the same order. There is not much happening. So it will be approximately unity. And you will be able to detect the if this ratio amplifies, grows beyond unity, uh, then that indicates that there is some extra energy coming into the signal over the uh, immediate vicinity of that cursor, wherever the central point of that window is. So that actually gives you the idea of so STA LTA ratio. It will, you can plot it, what, how it moves, and then you will see it kind of increases and then stabilizes, and then again it goes down. So this is STA versus LTA ratio, right? So wherever this starts, mostly at it will start at unity and then it will grow. So wherever this growth trajectory happens, that is detected as the start time, and wherever it goes back again to unity, you consider that as end time. So that's the process. And now how do I average? This is just the average of the signal. So I just keep on moving this window. So this is the signal, I keep on moving. So this is short term window and this is long term window, and this is the center point. So I will take 0.5 second on either side, take the data, and that will correspond to the point at the center of the window, right? And that's how we start with this. And STA LTA ratio will then provide us the starting of the event. So obviously it will depend on what is the resolution. So if I take the STA window to be 1 second, then I cannot resolve it any smaller than 1 second. So I will have the start time within the least count of 1 second. So that's how we start the event, detect the starting of the event. So not really very precise, but nevertheless it is better than losing all the information from the record, pre-event record. So once I do that, then I have some information that my, let's say this is the signal I get. So this is what I consider as the total earthquake signal. Right? Rest of that is just the background noise that is not of interest. So for further analysis, I need to take out this earthquake signal portion, and then take it to the further, take it for further processing. And that further processing will involve the first thing that we need. So to extract the earthquake acceleration signal and take up for further processing. Now lot of things happen before we go for further processing. Even for this case, we will see that even for this case, I mean, how do we get this? There are lots of things happen before this signal is actually recorded on this storage media. First thing is, of course, DAC. Oh, sorry, not DAC, ADC. Right. So this is analog to digital conversion. And that's where this useful frequency range comes from, because I guess all of you are familiar with this analog to digital conversion. The waveform, actual waveform is of course analog, but what we are doing is we are sampling it at discrete intervals. So when we say discrete intervals, so then natural question arises, how much at what how frequently do we need to sample? And it so happens that oh, this is, I'm sorry, uh, this is not the sampling. Natural frequency is of course 2200 hertz approximately. That's true, it's very high, so 100 to 200 hertz. But this useful frequency range actually comes from sampling rate. Sampling rate is about 200 SPS, samples per second. That is the usual sampling rate that you will find in these force balance digital accelographs. So once the signal is sampled at 200 samples per second or 200 hertz, so that's a cyclic thing, then any frequency above 100 hertz cannot be resolved. That's the Nyquist theorem, right? So Nyquist rate is 100 hertz. So that's the highest frequency that can be resolved when theoretical highest value that can be resolved if the signal is sampled at the rate of 200 samples per second. So factor of 2 is of course only for theoretical limit. Practical limit is about 1/3 of that. So that will be about 70 to 75 hertz. So that's a safe limit for 200 samples per second sampling. Now how do I the problem is what happens to frequencies above 100 hertz? Signal is of course there, it's an analog signal. It can comprise of any frequencies, whatever frequencies are there. I mean, there is no end to the it is endless, open-ended range, frequency range. So what happens to if I sample at 200 samples per second, then only 100 hertz can be resolved theoretically. So what happens to frequencies above 100 hertz? It so happens that these frequencies 100 hertz, they will be folded back into the range. So frequency of 101 hertz will be aliased as 99 hertz signal, and so on. 102 hertz will be aliased as 98 hertz signal, right? So in a way that will again uh, distort the signal. What we are recording is not really the true picture. There is no whatever we are recording, if 101 hertz comes around as 99 hertz or whatever frequency in the lower frequency range, then obviously it's not representing the true picture of the lower frequency which we should get. So in a way that is a complete corruption of the signal, and therefore what is required is uh, use of an anti-aliasing filter. Anti-aliasing filter during ADC. So this is built into the system, and this anti-aliasing filter is an analog filter. So what it does is, it is a low pass filter. So it will chop off all frequencies or remove all frequencies above a set threshold. So again, this threshold is user selectable, and usually it is made a function of or a fraction of the sampling rate. Not all users understand the nitty-gritties of discrete time signal processing. So this is a factor. Nyquist rate is very well defined, and depending on the sampling rate, how often this signal are to be sampled, and based on that this Nyquist rate is defined, and we take about 2/3 of the Nyquist rate as the usable frequency range upper limit, and that is set as the limit to which above that frequency all frequencies have to be removed first. So this is how it works. So in sensor, of course, generates senses the waveform. Analog waveform from the sensor, and that is passed on to ADC. Sorry, this is the total ADC that is passed through low pass filter, and then that low pass filtered signal is passed through discrete time sampler, and that is stored in the storage media. And from this storage media you take it up to further processing. Right. So discrete time sampler, of course, how does it work? So this is what up to this point it is still analog. The signal is in analog form. From this point onwards, it is discrete time sampled data. So this of course depends on the resolution of the sensor, sampler, ADC, analog digital converter. So most commonly used is of course the sample and hold circuit. Right, so what is done is you have the quantization levels. So the signal, whatever is the signal that happens at between quantized levels, it is held at that value, digital value, and it is held at that constant value. And next time interval, it may be at another quantized level or at another quantized level, and so on. So what you get is a uh, set of points where the signal is held constant over the time interval of sampling. So eventually you get this sample data which is just discrete values in time. So these are just the points, those are available at the quantized level. That depends on the resolution of the ADC, how often that is, how fine that resolution is, and that is what makes the uh, sensor expensive, or the quality of the sensor. So this analog filtering, the low pass filter, that is anti-aliasing filter, and this analog to digital converter, that total system is what is known as the ADC module, and that is actually the most expensive part, apart from the sensor, of this complete accelerograph assembly. And the quality of the data actually depends on how fine resolutions are being used for the ADC, and how good is the anti-aliasing filter, how effective it is in removing the frequencies. So what happens is, if I look at the frequency range, the signal might have the frequencies like this, some frequency range, and the filter will have flat response. Okay, I will just say the filter will have flat response only up to certain frequency. Right, so this is Nyquist rate, and this is probably practical practical limit of theoretical upper bound, or I would just say not FU, upper limit. Right, so this is the frequency response of anti-aliasing filter. So you can see that up to this hertz upper limit FU, the signal is faithfully reproduced. The frequency response is unity, so all the signals that are allowed, that are in this range from 0 to F upper limit, those signals are allowed to pass through without any uh, modification, without any truncation. Then there is a roll off period uh, frequency function, because theoretical ideal filter with sharp cutoff is not possible. So any physically realizable filter, any practical filter has to have a smooth roll off. So there will be some kind of transition zone, and the degree of this transition zone depends on the poles or the filter design. We will not get into the uh, details of design of digital design of these filters, analog filters, but it depends on suffice it to say that it depends on the uh, smoothness and sharpness of this roll off, how quickly it can get to zero. Depends on the order of the filter, so number of poles uh, of the filter, and typically we use 4-pole Butterworth filter. Usual choice of 4-pole Butterworth filter is generally adequate for earthquake accelerographs. Of course, there is no panacea that one setting can be used for any kind of signal, or it will work for any kind of signal. Uh, there are different filters for different purposes, but 4-pole Butterworth filter is generally found to be adequate for earthquake type of signals, and that is typically used. And once we have this low pass signal available, then it is sampled with this sample and hold circuit, and the values are provided in what we call as further processing raw accelerogram. Volume 1 or V1 data. So this is typically referred to as V1 data. Right, so V1 data, if you refer to any paper coming out from USGS, United States Geological Survey, V1 data they would designate it as V1 data. That is the raw accelerogram which has not seen anything beyond the low pass filtering, anti-aliasing filtering, and the uh, analog to digital conversion. No further, nothing extra has been done. Right, and of course that will contain information about the settings of these filters. So what are the filter characteristics that were used to generate this volume 1 data? That has to be preserved in the header file. So the uncorrected accelerogram or the raw accelerogram will contain the information about low low pass filters, sampling interval, etc., and the discrete time values of the data, that is sample and hold, that is coming out of the sample and hold circuit. And these would then be used for further analysis that we do. Now, that what is that further analysis that we need to do? So the first analysis first step after so processing of raw accelerograph. So now, before we do that, let us take a detour and consider a signal. Let us say we have this accelerogram as AT as a summation of Fourier series. Right? So I can do this for either in terms of sine and cosine, or I can just have a sine wave with a phase angle, so that takes care of the cosine component as well. So just as a illustration, what is the velocity signal, corresponding velocity signal? Corresponding velocity signal would be cosine term and with a scaling factor of 1 over omega I. So every frequency component is scaled down by the frequency omega I. And what is the displacement signal, derived displacement signal? Again, it is going to be minus AI omega I squared sine omega I t plus phi I. Now, this provides us a very interesting insight into the nature of signals and changing frequency composition. Let us look at two frequencies. Two frequency components during this process of deriving velocity and displacement from acceleration. Right? So let us say omega 1 is equal to 0.01 and omega 2 as 10.0 and A1 as, let's say, both unity. So equal strength, two frequency components of equal strength. So acceleration looks like sine 0.01 t plus phi 1, let's say, I would just say phi 1 is equal to 0 and phi 2 is also equal to 0. Just to keep things simple, plus sine 10t, right? So velocity becomes 1 over 0.01, so 100 sine 0.01 t plus 0.1, sorry, cos 10t. This would be cos. Displacement would be again 10 raised to the power 4. Okay, this is getting little very large number, it will be difficult to plot. So let me just consider the frequencies as 0.1 radian per second. So then this will be 10 and this would be 100 sine 0.1 t plus 0.01 minus 0.01 sine 10t, right? So now let us try to plot these functions. So Ax is defined as sine 0.1 times x plus sine 10x. Vx is defined as 10 times cos of 0.1 x plus 0.1 times cos of 10.0 x, and d x is 100 times minus times sine 0.1 x minus 0.01 times sine x. Set grid, set x range 0 to 10. Plot AX BX. So this is what it is. Can you make out the difference? So let me just plot them individually so that you can. This is the acceleration. Set samples. Can you see what is happening here? Any ideas?
No damping is there.
Of course, there is no damping, it is pure sine wave. But what you need to observe that this is a high frequency component, right? So 10 radians per second signal riding on top of low frequency component, right? So this 0.1 radian per second is the baseline for this 10 radian per second component. Right, but the signal is still predominantly that you see is 10 radian per second for the acceleration trace. But when I do this for the velocity,
for acceleration trace 10 radian signal
so on top of it I plot, where did it go?
ये क्या है ना
So let me just say plot
.51
So this is the signal. Again, it is predominantly now the low frequency component is getting more prominent, high frequency component is getting less prominent, but you can still see that the high frequency is riding on top of the low frequency component. You can still see some presence of high frequency component. But when I do this for the displacement, then the high frequency component is totally gone. You can't detect it. It's a completely low frequency, right? So the high frequency signal, so the point is you need to look at these two aspects very clearly, very carefully. Acceleration is primarily, it is dominated by high frequencies. Low frequencies only provide the baseline about which the high frequencies oscillate. But the low frequencies in the displacement, it is the lower frequency which govern. High frequencies do not appear at all, they are unrecognizable. The signal is very much there. If you see our derivation, the signal is very much there, but its weightage is grossly uh, suppressed. Right? It is this displacement lower frequency is amplified by 100 times, whereas this high frequency is de-amplified by 100 times. So this effect is completely uh, absent. It cannot be or insignificant, so to say. The velocity is somewhere in between. You can see both high frequencies and low frequencies, uh, but you will see still the differences. Acceleration, it is the high frequency which dominates, the lower frequency only provides the baseline. Now that's the problem. If I do, if you look at it from what we were discussing earlier, if I try to do some kind of baseline adjustment here of this trace, there is no baseline here. I don't have zero line here. So if I try to do a baseline correction, something like this, baseline adjustment, something like this, acceleration trace may not be influenced significantly. We may still get more or less similar acceleration, but the displacement will be influenced dramatically. Right? So the implication of this is baseline adjustment will have dramatic effects, dramatic influence. I'm using this dramatic word intentionally. I could have, I mean, because it gives more emphasis than significant. Significant is less emphatic. Dramatic influence on the derived velocity and displacement traces. And this is something that we need to appreciate before moving further with the baseline adjustment and volume 2 processing of the record, because whatever we do is going to, it will not have significant, it will not show up in any appreciable effect to any appreciable extent on the acceleration trace. You may find that acceleration is same. I mean, whether I use the raw volume 1 record or whether I use the volume 2 record, I see the same acceleration, but more or less same acceleration. But if I try to derive the velocity and displacement signals from those two, there will be, those would be poles apart, so to say. I mean, there is no correlation, there is no similarity. You will not be able to find any similarity between the displacements derived from raw accelerogram volume 1 data and the displacements derived from baseline adjusted volume 2 data. Volume 2 data, of course, will contain the velocity and the displacements, derived displacements. Right? So, in our next week, next session, we will discuss the baseline adjustments and also start playing with numbers using octave, GNU octave. So I will stop at this point, and any questions, please, we can have a discussion.
Actually, we are for our seismic design parameter studies.
Yes, sir.
Generally, uh, we are using this acceleration values only. We are
Yes.
estimating the acceleration and spectrum also. Of course, we are giving this velocity and displacement also. But generally, the spectrum we are giving with this. And like suppose if we are we are attenuation law we are designing, then for estimation of the acceleration. So in that
Okay.
case, uh, if even we do not apply this baseline correction, I think it will not have much impact.
Baseline correction will influence, as I showed in this case, it
Mhm.
will have impact on the low frequency components.
Yeah.
So,
Yes.
I mean, when we took a look at the ground motion prediction equation or the spectrum, the so when now PGA is of course only one point which is at the rigid zone or zero period acceleration, but we need to characterize the entire spectrum over the
Yeah.
complete natural period. So as
Mhm.
we go beyond 5 seconds, the influence of baseline will become apparent on the values that we compute. The response
Mhm.
spectrum beyond 5 seconds will begin to be influenced by the baseline correction. So it is not hypothetical that it will only affect the displacements, because it is the frequency composition that is getting affected by the baseline correction, and
Yeah.
that frequency, that alteration in frequency composition will begin to influence our uh, uh, design spectrum or the spectrum that we compute uh, beyond 5 second natural period.
Mhm.
Up to 5 second,
Yeah.
more or less safe, but beyond 5 second it is of course for hydropower it is not of concern, but beyond 5 second is a major concern for industrial installations which have many uh, pipes running through the systems. So piping systems, they are typically long period
Yeah.
systems. So they will
Yeah.
be significantly influenced by the characterization of spectrum beyond 5 seconds. So for hydropower systems, of course, even
Yeah.
for
Yeah.
earth dam, the natural period will never go beyond 3 seconds, I would say.
Yes. Yes.
So concrete dam, of course, it's much
Mhm.
shorter. Even
Yeah.
but
It is.
for even
Yeah.
earth dam, I don't think it
Yes.
will go beyond to 3 seconds.
Yeah. Actually, in most of the cases, we are getting zero point 0.7 second or 1 second like that.
Mm-hmm.
Actually, like in case of Subhansri also, it was only around point 0.668 or something
Yeah,
uh, second.
right. So, so maybe not really a matter
Yeah.
of concern for hydropower structures, but since we are doing this course, so let us
Yeah.
go the whole hog and cover the
Yeah.
subject matter in its entirety rather than keeping it
Yes.
very domain specific. And
Yes.
we have time at our hand, so
Yes.
every
Yeah.
weekly engagement allows us to have a uh, leisurely discussions about the issues involved, and there is really no need to rush through the topics. Okay, so I'll stop here, and next week we will start with the uh, baseline correction, baseline adjustment that we do on these volume 1 data, and also start with working with numbers. I'll try to compile a set of exercises that you can work uh, after the next week's lecture. Okay.
Okay. So thanks a lot again,
Thanks.
and it was a very good and interesting lecture. And
Thanks.
I think next lecture again we will have the similar very good lecture from your side. I'm again thankful to you
Thanks a
for
lot.
this
Thanks a lot, sir.